Yeah, so basically we have this very, for very good reasons, we have a very Earth-centric view of what is habitability, right? Because Earth is the only planet that we know of that can sustain life. So we tend to think, okay, Earth is kind of the pinnacle of habitability. And a lot of times we approach the question of habitability from like, how much like Earth are these other planets? But there's this idea that, things could be better than they are on Earth. Like Earth might be a kind of middlingly habitable planet.
Hello from the children of planet Earth.
Super. Nora, thank you so much. Nora's Guide to the Galaxy. Is it Dr. Nora now?
It is Dr. Nora now, yeah.
Dr. Nora's... Are you going to change it to Dr. Nora's Guide
I probably am not, but...
Okay.
But it is nice that I could if I wanted to.
Absolutely. I'll put Dr. Nora on the top of the video because people always think it's fancy. And it is fancy, so well done.
Thank you. Very good. Thank you.
Yeah. If you could maybe just start off with just sort of your name and what you do.
Yeah, so I'm Nora. I'm an astrophysicist, and I just finished my PhD at the University of Chicago. My specific area of research is Exoplanet Dynamics, which is just how planets interact with one another via gravity. And there turns out to be like a lot of really interesting implications, even though you might think like that's all been totally solved. And I love doing science communication. So Nora's Guide to the Galaxy is my space and astronomy science communication. And I do that all over social media. So TikTok, YouTube, Twitter, Instagram, all that fun stuff. And I've been having just so much fun doing that. And I'm currently looking for a job.
Nice. Awesome. I will put all those links below. I have just read the three-body problem. So I'm all about orbital dynamics.
Yes.
At the moment.
I read that series, and like the first book is not particularly accurate when it comes to the three-body problem, but I just thought it was so cool to like see what I study like as a plot of a book. Like I just had a ton of fun with it, and I thought the series was really good.
Okay, so the next books are more accurate then? Or
well, the next books get a little bit farther away from known science, I would say.
Okay. I've been interviewing a couple of science fiction writers, and actually, like some science fiction writers are first scientists and then have become science fiction writers, and those are generally the ones that I prefer in terms of the accuracy.
I actually also write science fiction and fantasy in my free time. And I actually am the opposite. Like, even though I'm a scientist, when I write science fiction, it's totally like space opera, faster than light, like spaceships, like screw physics.
Sure. I mean, a question I've just been asking people recently is, what does humanity look like in 1,000 years?
I mean, I definitely think, not to sound... I'm not like trying to be an Elon Musk fangirl, because I'm not, but I do agree with him that I think the future of humanity is to be an interplanetary species. I'm not sure that necessarily his route is the way that we need to go, but I do think by 1,000 years from now, we'll have colonized more of the solar system. And gosh, I really wish I was going to be alive to see it. So I think that will be kind of a big change. And I don't even know if I could really say what that would be like, because how could it change when, humans are living on different planets? Like, what would that even do for our society? I don't know. I think it's a really interesting question, though.
Sure. Okay, let's get into the physics and planetary stuff. I'll start off with an easy one. Why is gravity so weak?
Gravity is weak. I will. You're correct. But at the same time, it's also incredibly powerful, because it operates basically over infinite distances. And so even though it's relatively weak compared to the other fundamental forces, it still is shaping the entire universe. And we have, structures at scales of galaxy clusters, which are gravitationally bound. So even this weak little force is having, massive implications for what the universe even looks like. As for like why it's so weak, I think that's still probably an outstanding question, because a lot of the details of gravity are still being actively worked on by physicists and haven't been kind of folded into the other three fundamental forces, which kind of have all been unified in a single theory. So gravity is still kind of the pebble in the boot there.
Sure. I mean, it's not one of my questions, but like, Could you give us just a brief thing that like, what is cool about orbital dynamics? Tell us something that you find super interesting about like how planets revolve around each other.
Something that I think is really interesting and is kind of relevant to the work that I have done, so that's probably why I find it interesting, is that even these really, really small effects that might seem very negligible sometimes aren't. And that can take a really long time to actually see the effects of that. There was a paper recently that, and I'm sorry, I don't remember who the authors were, but I thought this was fascinating. They found that if a star flies by a planetary system, that can, kind of gravitationally nudge the planets in the system. But they found that sometimes the actual effects of that wouldn't really start to show until many millions of years after that star was long gone. So like it was having some minor perturbation on the system that was like keeping it in a quasi-stable state. And then eventually you actually get these big changes, but it takes a really long time. And in fact, there's a lot of chaos in planetary systems because of gravity. And like even in our own solar system, like we don't know what the future of Mercury is going to be because it's chaotic. So it diverges basically in the future. But, not like the near future. We're talking millions of years from now, but I think that's fascinating.
What could happen to Mercury in millions of years?
Yeah, Mercury could go unstable. It could be yanked out of the solar system. Basically, its eccentricity, which is kind of how non-circular the orbit is, can get excited in some cases. And when we're talking about like what the outcome is going to be, it really depends on like literally millimeters in the current location of Mercury. So, I mean, we just really don't know.
And is a lot of this work done sort of computer modeling of what these systems could do, or people sort of still like theorize of what could happen and then try obviously then work it out from there?
Yeah. So computers are like a huge part of orbital dynamics now. Computing power has just gotten so cheap and available that you can really use it a lot more than we could in the past. And so a lot of my own work has been doing that. There's a lot of different open source packages out there to run code to do these n-body simulations. And you can always, kind of choose what you're including in these simulations. So you could just run like strictly gravity, no other like effects, but you can also add in things like general relativity. I mean, that's gravity, but Newtonian gravity, you can add in general relativity. You can add in like effects from tides and other forces that might be present in the system. But analytical solutions are still definitely used because even with like, there is a lot of computing power available, but it still gets very cost prohibitive if you want to do, for example, over like a really large range of system parameters or a lot of particles. It really slows down the process. So yeah, analytical solutions are definitely still used. People come up with various approximations to try and explain the motion of planets because, of course, the three-body problem, the reason it has that name is that it is unsolvable. Like mathematically, it has been proven that it cannot be explicitly solved. So we have to come up with ways of approximating it.
Wow, fascinating. In terms of this project, like, would you know what it takes to get a spaceship out of our solar system?
So I have not done that myself, but definitely you could, you could consider that to get a spaceship, to a destination requires some amount of delta V, which basically is the measurement of how much you're going to have to change the velocity of the spacecraft to get it to do what you want. Actually, getting out of the solar system takes a lot less delta V than maybe you might imagine, because you really just need to kind of escape the sun's gravity. But things like going to other planets actually takes a lot more delta V because you have to match their orbits. And so, for example, actually going to Mercury, I believe, takes like a ton of delta V, like way more than it takes to get to like Venus or Mars, just because it's so close to the sun and you have to get in and you have to get up to its orbitals.
Super fascinating. Cool. Let's talk exoplanets. Where do we begin with exoplanets?
I mean, we begin in 1992 with the very first one that we ever found, which is, I mean, that's crazy. That was within my lifetime. Like, we literally didn't know of any exoplanets when I was born, and now we know of thousands and thousands of them. So it's really exciting. I think it's still a young field. It's still a new field, and I think it's one that really captures not just the interests of scientists, obviously, but even the general public, because I think people have kind of that innate wonder about what other planets might be like and what other solar systems might be like. So, yeah.
Sure. I think just for me, even just the idea that like almost every star has exoplanets, and that there are more planets that we know of than there are stars, and there are a lot of stars out there.
Yeah.
So
Yeah.
like just
It's crazy. And we didn't know that. I mean, people had like hypothesized that, but we really had no idea. And when we started discovering exoplanets and just how ubiquitous they are, and it really is, almost every single star has exoplanets. So to me, that's exciting. That's great news. That means there's way more planets out there than we could ever even hope to learn about. So, and there's, you know, we have a lot of planets. We have 8 planets in our solar system. So like we thought we knew what was going on with planets. And then we started finding exoplanets and it was like, no. And so it really helped us like understand a lot more, not just about astronomy and like how stars form, because planets generally form, you know, kind of from the remnants of the stellar disk that the star formed in. But also about, you know, our own solar system and about planetary science. Like the most common type of exoplanet is this planet called either a super Earth or a mini Neptune. So basically it's in between the size of Earth or Neptune. And we don't have any of these in the solar system. There's kind of a gap in the size range between the terrestrial planets and then the giant planets. But these are the most common type of planets that we see in other systems. So why don't we have them? This is kind of, these are the questions that are being actively researched now. And we wouldn't have even known to ask that, you know, a couple decades ago. So it's really exciting.
Fantastic. Okay, so let's go through the story. So there's a whole lot of dust in the universe. Some of that dust starts clumping together. A star gets formed. The rest of the dust is in a disk. Why is it in a disk?
Yeah, we see disks all over, and it's basically because of angular momentum. So when you have material, it kind of falls in, you know, spherically, as you might expect, but all of that material has a little bit of angular momentum, and angular momentum is basically conserved. So the way that it works out is basically a disk, a flattened disk, for a given amount of angular momentum has the lowest energy state. So it's kind of this like nature seeks the lowest energy state type thing. It's kind of the simple way of doing it. How I think about it.
And then, so from this disk, you have things starting to come together. They'll start collecting other dust and matter and stuff.
Yeah, so there's actually 2 like main mechanisms that we think cause planets to form. So the first is called core accretion. And so basically the idea is that, you know, in a young protoplanetary disk, you do start to get these kind of, the dust like clumps together into little pebbles, and the pebbles clump together into little planetesimals, and the planetesimals clump together into these, basically what we would think of kind of maybe as like a terrestrial planet. But because it's still early on in the disk, there's still a lot of gas around. And so now you have this massive object. So the gas is attracted to that, right? Because of gravity. And so it starts to accrete all this gas, which makes it more massive, which makes it accrete more gas. And so this is how you get planets like Jupiter and Saturn, these gas giants, because they start with these, you know, terrestrial cores, you know, maybe 10 times the mass of the Earth or something. And then they create all this gas on top. But eventually the gas in the disk, it dissipates, it goes away, it doesn't stick around forever. And so you might get smaller planets if they form kind of towards the end of when the disk is around, because they won't accrete as much gas. And then the terrestrial planets, usually we think of them as forming after the disk is gone. Usually in a region of the disk, like the inner portion of the disk, where there's just not really much gas and ice anymore. So the like hot parts of the disk. And then the other one is called gravitational instability. And that's basically, you kind of think of it as like the same way that a star forms, whereas like you just, in an outer portion of the disk, you just have enough gas and dust that it's heavy enough that it just collapses in on itself and kind of directly creates a planet out there. So.
Okay, let's talk systems. Alpha Centauri, that is, as I understand, 2 stars or 3 stars.
3.
And there is a potential for a planet that's in the habitable zone, and that is our closest star, and that's 4 light years away.
Yeah. So the Alpha Centauri system is a triple star system, and the star that's actually closest to us is kind of the single one. So there's like 1 star kind of off over here, and then 2 stars that are like close together, and then all of them are orbiting one another. Yeah, so Proxima Centauri does have planets, and one of them is in the habitable zone of Proxima Centauri. Now, Proxima Centauri is a red star. It's at M dwarf, so it's very dim and cold compared to the sun, which means that the habitable zone for Proxima Centauri is much, much closer to the star. So I forget off the top of my head what the orbit of the planet is, something like 11 days around Proxima Centauri. So we're talking very close to the star in order to get enough light and heat from that star to potentially have liquid water on the surface. But of course, we do not know if that is the case.
Is it tidally locked, that star?
Yes.
The planet?
I believe so, yes. we would expect it to be tidally locked, I would say.
Yeah. What is tidally locked?
Yeah, so tidally locked is the best example, I think, is the Earth and the Moon to kind of understand this. So, on the Earth, we always see the same side of the moon. Or you could think of that on the other way around. On the moon, the same spot is always kind of beneath the Earth. And so the same thing kind of happens for planets and stars. So it's called the substellar point. So basically the point on the planet that the star is kind of directly shining on is constant. It doesn't really change. And this happens over time because of the forces of tides, basically. Won't go into the details because there's some math and stuff. But yeah, basically planets aren't perfect, points. They have extent and they deform and move, and that has implications for their orbits.
Can we talk about what are the ways we find exoplanets?
The very first ways that we did, the very earliest ones, were called radial velocities. So this is really cool because a lot of the ways that we detect exoplanets are very indirect because planets are very tiny and very dim. So it's not like we're going out and just like looking at planets. So a lot of times we look at the star instead. And so with radial velocities, you look at the star. And now we usually say that like a planet is in orbit around a star, but technically what's actually happening is that both the star and the planet are in orbit around each other, around their center of mass. So the center of mass usually lies within the star, but it is not the exact center of the star. And we see this in our own system too. It's called the barycenter of the solar system, and it moves over time. And so basically, if we look at the star really carefully, we can actually detect that motion as the star is like just kind of moving a little bit in its own little orbit because of the planet. And so if we detect that motion, then we can be like, hey, there's a planet there, and we get some information about the distance and the size of the mass of the planet. So that's pretty exciting. And that was kind of the first big one, but this kind of been overtaken now by transits. So transits is a similar thing. You're looking at the star. But now instead what's actually happening is that the planet is kind of passing in front of the star. So this also happens again in the solar system. The transit of Venus across the surface of the sun is actually a very famous transit because it only happens every 200 something years, I think. So it doesn't happen very often. You have to get quite the right alignment. But we can do the same thing with planets and other systems, and it causes the light from the star to dim just a little bit because you're blocking just a little bit of the light, like really tiny amounts, usually in the range of parts per million brightness and flux. And again, that gives us information about the planet. How often we see that light dip tells us, how long it takes the planet to orbit, and then how much light gets blocked tells us the size of the planet, the radius of the planet, assuming we know the size of the star. So those are kind of the two main methods, but there are several other ones, including we can actually directly image a very few number of exoplanets. Usually these are going to be very massive, so bigger than Jupiter usually, and very young, because when planets like that form, they're very hot when they are very young and they cool down over time. So when we're directly imaging those planets, we're actually looking at their own light. So this would not be like looking at like the Earth, because the Earth doesn't emit enough light to really be detected like that. We only would be visible in reflected light from the sun. But these planets are visible from their own light. But that's kind of a big goal of the field, is to be able to image exoplanets in reflected light. That would be really exciting, but it takes a lot of work because, like I said, planets are very small and they're not very bright, and they're right next to things that are very bright, the stars. And so you not only have to be very sensitive, but you also have to be able to do a lot of contrast, like 1 billion time difference in like brightness between the star and the planet, at least. So it's a really challenging problem for observational astronomy. Gravity via microlensing, which is really exciting. It's basically the concept that mass warps space-time, and it can create these little lenses out of space-time, basically, and we can detect planets that way. And I'm trying to think, what am I missing? Astrometry. So this is the same idea as radial velocities. So the star, right, is moving, and we can see the radial velocity. But radial velocity, the radial part, means that it's radially to our line of sight. So we are actually using the Doppler effect to detect the motion. Whereas astrometry is looking instead like kind of face on a system and actually measuring the motion of the star on the sky, and then inferring the existence of a planet. And that is really difficult to do. You need extremely precise measurements of the star's location. And we have detected a few planets via astrometry, but we've not discovered any planets via astrometry, if that makes sense. We've looked for planets that we knew were there from other methods, and we were able to find them. But that should change in the next couple of years because ESA's Gaia mission has been measuring these types of motions for stars, and they are expecting I don't think the upcoming data release, I think it's the final data release, they're expecting to announce potentially thousands of new planets that were discovered via this technique. So that is really exciting to come. We're really all really excited about that. I think that's most of the methods, the main ones. And the crazy thing is, I mean, they're so far away, but also they're so not far away in like an astronomical sense. So like we can only detect planets that are like in our little neighborhood in the galaxy. There was a paper last year, I think, that potentially saw a transit of a planet in another galaxy, which has not been done before. And I don't think they were able to like 100% confirm it. And it was a very weird situation because it was like an X-ray binary. It was like not a normal star, which was the case because it had to be for us to be able to see something that bright from so far away. But in general, yeah, we're only seeing planets, in our side of the Milky Way, pretty much.
Yeah, sure. Are you excited about James Webb?
Definitely. Yes. I mean, James Webb has been in the works for so long. And I feel like I've just been hearing about it. And it's crazy to me that James Webb is out there now. It's like almost ready to go. The launch went so perfectly, beautiful launch. Like everything has gone just flawlessly, which is kind of shocking given how many issues there were in the development portion of it. And I was like not totally confident, but they proved me wrong for sure. And I think from an exoplanet's perspective, what's going to be really exciting about James Webb is that it will give us a lot more information about the atmospheres of exoplanets, which we can do a little bit right now. But if you ever look at like the data that we have on exoplanet atmospheres, it's like 4 data points like spread across a long way, and they're trying to fit a model that's like, like very detailed, and you can't really do a lot with it. But with James Webb, we'll start to get a lot more resolution on the spectra of atmospheres from exoplanets, which is really exciting.
Absolutely. Obviously, again, for this project, sort of the interest is definitely around sort of, and for I think a lot of people, but like life on other planets. And, could you explain sort of how we could spot potentially that an exoplanet has life on it?
Yeah, so I don't think James Webb is going to be able to do this definitively. It might be able to find some interesting targets that we think have some signs of life. But being able to definitively prove the existence of life is definitely a difficult problem and one that is still being worked on. Like what would constitute a biosignature, like a confirmable biosignature? There's some things that would certainly be promising as far as life goes. And some of them, you might think like, oh, like oxygen. And yeah, definitely oxygen could be a biosignature, but there are ways to get oxygen in an atmosphere without biology. And so you have to, take that into account. And kind of a lot of times it's the existence of multiple components in the atmosphere at the same time. So one common example is kind of the presence of oxygen along with the presence of ozone does tend to be a little bit more strongly linked with just a biological origin rather than possibly abiotic origins. But again, I don't think that's like 100%. Like there's probably a way you could come up with it. And basically any sort of atmospheric signatures that require some sort of disequilibrium, right? So the Earth's atmosphere is not in equilibrium because life on Earth is constantly, putting things into the atmosphere. And so it's not what it would look like if there was no life on Earth. So that's the kind of thing we're trying to look for in other planets, but it's really hard because, life might not be exactly like life on Earth. The Earth's atmosphere did not always look like this. If you go and look at a prehistoric Earth atmosphere, it looked very different, even at points in time when there was life. And so, yeah, it's a really challenging problem.
Sure. Technosignatures, is it possible to find a technosignature on another planet?
Yeah, it definitely could be. And that would be really exciting because it would be probably less difficult, I think, than just this atmospheric biosignature where there would be a lot of room for interpretation. But of course, with a biosignature, you could be looking at bacteria or something. It could give you a lot wider range, whereas a technosignature is really one very specific type of life that we would be looking for. And again, obviously, you would have the same issues of that. We don't know what other life would look like. We don't necessarily know what other technology would look like. But we have some ideas if it looked anything like ours that we could look for. And this includes things like looking for signs of artificial lighting on other planets, kind of like street lights, like what they might look like and how much they would have to be on a planet in order to be detectable. Things like, I've heard people talking about looking for things like glint. So like the reflection of the light, and obviously, again, this is not within our current capabilities to do, but hopefully, in the near term future, and how that would change depending on the surface of the planet. So like if you had buildings and glass, like that would look different than if you just had like a rocky natural terrain. And then of course, there's obviously technosignatures like that they might be actively sending, right? So looking for someone else out there in the universe that is signaling, hey, we're here, because we've done that. Not a lot, but we have done that. And so, those kinds of things are being looked for. Yeah.
I'd heard that like people were looking for a Dyson Sphere or for basically a star that had structure around it, and you wouldn't see the light in the star, but you'd still see the heat, I think it was.
Yeah. So definitely there's like different proposals for things that, other civilizations might do, particularly ones that are more advanced than us. And so every civilization, as far as we can imagine, would need energy. There's really no way to have a civilization without energy. And so one potential way to get a lot of energy that you might need for a very advanced civilization is to build something called a Dyson Sphere, which basically, I don't know, kind of think of it as just like a solar panel that encases the entire star. So you're just really like, harvesting all of that energy from the star and using it however you want. And yeah, that would have a signature that we could observe. We have not seen it yet. People have been looking, but yeah, there's like a whole thing called the Kardashev scale. I think that's what it's called. But like different levels of civilizations, and there's different hypotheses about what that would look like. And in fact, it has been an argument against the existence of other civilizations that we haven't seen, for example, any of these civilizations that have basically taken over an entire galaxy and harnessed the like energy sources of the entire galaxy, because some people think that would be a kind of inevitable outcome of a civilization. I'm not sure that I'm convinced, but it is something that people have argued. So
super habitable exoplanets. I just learned about this. Actually, I'd learned about it like the day before, and then I saw you'd posted something on Twitter about something about exoplanets. I was like, that's when I first said like, cool, this is a good thing. I've just learned about this and I want to learn more about this. Tell me about super habitable exoplanets.
Yeah, so basically we have this very, for very good reasons, we have a very Earth-centric view of what is habitability, right? Because Earth is the only planet that we know of that can sustain life. So we tend to think, okay, Earth is kind of the pinnacle of habitability. And a lot of times we approach the question of habitability from like, how much like Earth are these other planets? But there's this idea that, things could be better than they are on Earth. Like Earth might be a kind of middlingly habitable planet. So there could be planets out there that have, for whatever reason, better circumstances for developing life. And this could be in a wide range of things. So this could be like the properties of the planet itself. It might just be like the gases that are present in the atmosphere when the planet is formed, or the size of the atmosphere, the size of the planet, the continental configuration. So actually continents seem to be very, very important in habitability. I'm not a planetary scientist myself, so I don't want to like totally misspeak here, but I've been to some talks, and there's this concept of upwelling. So basically, the continents really help us cycle nutrients from the ocean onto land, and from the bottom of the ocean to the surface of the ocean where the sunlight is. And so this is like seen as probably somewhat important, but we don't know for sure if this is like 100% necessary, but it could have implications what the different continents look like for habitability. And actually, I recently, I submitted a paper that is I'm working on corrections right now, so hopefully it will be published sometime soon. And this actually approach did talk about super habitable planets, but from a different perspective, and that is the system that the planet is in. And so, the Earth exists in the solar system, and we still don't know the extent of how much that impacted the fact that we have life on Earth. Like, for example, the presence of Jupiter and Saturn. And so what I was looking at was how giant planets in a system might make an Earth habitable or uninhabitable, either via destabilizing the planets or by affecting the eccentricity of the orbits. Because as an orbit gets more eccentric, it changes the climate on the planet, and that changes the habitability. And one thing that I did find in this paper is that, in general, we might kind of like naively think that not having giant planets, at least from this perspective, would be beneficial because no one is going to destabilize you. So you could just have a planet in the habitable zone and it would be kind of perfectly habitable. But actually, it's possible that having giant planets in the system can actually make planets super habitable because it can extend the range of the habitable zone by exciting these eccentricities. So there's a lot of different ways that we can actually kind of approach this question of habitability. And yeah, Earth might not be the pinnacle and the be all and end all of habitability. There can be planets out there that are just incredibly well suited for the formation of life, but we don't know yet.
and like sort of these gas giants, would they also like stop or sort of take on meteors that potentially could have hit habitable planets? Like, do they also form that part of it where they're going to protect, almost like in some ways, the moon does?
Yeah, so that's like a really interesting question, and one that I'm very interested in, but I did not get a chance to address in this paper. But yeah, definitely the giant planets would have implications as far as the formation of the planets, in particular, in one way, the what's called water delivery. So basically the amount of water that makes it to Earth or to an Earth-like planet in another system. And this definitely has a lot of dependence on the existence of the outer planets because that water usually comes from ice. So it has to come from the outer solar system and somehow get into the inner solar system because the water that's actually in the inner solar system when the terrestrial planets are forming would evaporate. It's just too hot. So you have to kind of deliver this water after the formation of the terrestrial planets in some way. And the exact influence of the giant planets, I think, is still being investigated. But for example, I think depending on the formation mechanisms you assume and how the planets form, and sometimes without giant planets, you might actually get too much water because the giant planets actually kind of act as a barrier for that water getting in from the outer system. And without them, maybe you would end up with these really, really water-rich planets, which might be a good thing for life, but it might be a bad thing because, like I mentioned, continents seem to be relatively important. And if you had too much water, you wouldn't have continents. You would have a water world. And so kind of TBD on how that would affect. And then post-formation, we see this in our solar system a lot, the question of, is Jupiter protecting us from, being destroyed by an asteroid impact? For a long time, I think the general idea was yes, that Jupiter was kind of our protector out there in the outer solar system. But there was actually a series of papers called Jupiter, Friend or Foe by Horner. I don't remember when these were done, probably 10 years ago. But anyway, they investigated this idea, and they actually found that Jupiter is slightly more of a foe in that, so there's multiple sources of asteroids or comets that could impact the Earth. And Jupiter protects us from some of them, but it actually makes some of them, it actually causes some of them, basically. So it's a little bit of a wash, and Jupiter is maybe not as wonderful as we thought when it comes to that. But definitely these are all like things you would need to take into account when it comes to considering the habitability of a planet.
There's an exoplanet that has more water in our solar system. I forget which one it is. Than there is on Earth. It's a moon. There's a moon.
Oh, yeah. So several of the icy moons have lots of water, but that water is often, it's frozen. So, but there's usually subsurface oceans beneath the frozen part. So those are some of the most exciting targets for astrobiological searches in the solar system, and really exciting, I think, in the near future because we're going to really learn a lot. So we have Europa Clipper coming up. So we're going to NASA sending a mission to Europa, which is one of the icy moons of Jupiter. ESA sending a mission to the icy moons, and then the Planetary Science Decadal Survey, which just came out last week, identified the top priority for a flagship mission as the Uranus orbiter, but the second priority was an Enceladus mission, which is a really exciting target for astrobiological searches because it has these plumes of water that's just being sent out. So we could easily search those for life without having to drill through all the ice. So yeah, really exciting. And I think we'll start to get some more answers in the next, couple decades.
Do you think we are alone in the universe?
No, I definitely do not think that we are alone in the universe, but that does not mean that I think we are going to ever know whether or not we are alone in the universe. I think those are two different questions. But just like statistically, based on the size of the universe, I think it would be almost impossible for Earth to be the only planet that managed to create life. That just seems absurd to me. But we are limited by how far we can look for things. We're limited by the travel time of light, and limited by our understanding of what we should even be looking for. So whether or not we can find other life, I'm not as sure of. That really depends on how easily life forms. Because if life is really, really difficult to form, then, maybe the Earth is the only one in the galaxy. That still seems a little unbelievable to me, but it's possible. But if life is really easy to form, maybe we'll find life in the solar system. We don't know yet. So I think depending on kind of where on the scale it falls, how likely we are to actually find other life. But I definitely think it exists. It might exist in ways that we can't access.
Sure. From what you know about exoplanets and their formation, obviously life is affected by how our star, the color of the star, all of the stuff that sort of goes into where we are. Any idea on what that life could look like?
Yeah, that's a really interesting question. Because a lot of life on Earth, life on Earth evolved to fit the conditions on Earth, right? So our eyes are sensitive to visible light, which is, we call it visible light, which is the portion of the spectrum where the sun peaks, where its emission peaks, because that's, that makes sense. And that also happens to be what the atmosphere is transparent to. And, we take advantage of photosynthesis, takes advantage of the sun's light and how that, is delivered to the surface of the Earth. And so how would that look different if, you were around an M dwarf, which has a very red spectrum? Would the plants look different? Like, would you be able to have photosynthesis? This is questions that people are, actively researching and trying to figure out. And I think it's really interesting. And I don't know what the answer is. Maybe it all looks relatively similar. Maybe, we see it a little bit on Earth, right? I'm not a biologist, so forgive me if I'm misspeaking, but I think it's like crabs or something. Like crab-like creatures have evolved separately, independently, like multiple times on Earth. So like maybe when life evolves, it just kind of tends to follow a similar pattern regardless of kind of the environment. Like maybe some small adaptations to the environment, but maybe life will look relatively similar to what we have on Earth despite different conditions. But maybe it will just be completely different. Maybe it won't use carbon. Maybe it's not carbon-based life. Maybe you start getting like sulfur-based life or whatever. I think people are studying this kind of stuff. So I think it's exciting. I would love to know.
We find in another exoplanet, we are able to communicate with another intelligent life from that exoplanet. What would you like to know from them?
This is such a nerdy answer. Okay, I think I would want to know, their understanding of physics, because like it seems like something that should be relatively universal. And I'm curious how another civilization would interpret it via their lens, and if it would even be understandable to us, and whether having a totally different perspective on it would help us understand things better or different things. And kind of this gets at the question of is math invented or discovered, right? And so similarly with physics, how did they discover it, or how did they invent it? And is that translatable? And what does that tell us about the universe?
Nice. I like it. What is the most exciting thing in your field, do you think, over the next couple of decades?
So I think, my field has been very lucky to get a lot of support from NASA, from the public, from funding agencies. And so it's really exciting. And I think there is going to be a lot of resources available to our field. And I think in particular, kind of the next big flagship space telescope. So the astronomy decadal survey came out last November, October, November. And basically they identified the top priority for the next flagship space telescope to be one that is kind of optimized to detect exo-Earths. And I think that's really exciting. I think that's kind of, in a lot of ways, kind of the holy grail of exoplanet science. And we'll learn so much. And I'm really looking forward to that.
Awesome. Interests outside of space sciences?
Yeah. So that's a great question, because I think a lot of people think that as an academic, you have to be like 100% consumed by your work, which I definitely am not. So I like to bake. I am an avid baker. I like to run, not very well, but I do like to do it. I did my first and only marathon last year. I think I will stick to half marathons or shorter from here on out. That was rough. Like I mentioned earlier, I'm also a writer. I write science fiction and fantasy. I write short stories and novels. I have not had any novels published, but I have had a couple short stories published. And I very casually play the violin. I actually just bought myself a new violin as my PhD present to myself. So I'm really excited to practice, because my old violin was damaged a few years ago, so I haven't played in a while. Yeah, I don't know. I have lots of interests, I guess.
Advice for any aspiring scientists?
Yeah, so if you're interested in science, I would definitely encourage you to pursue it, and to not be deterred by people that might tell you that you can't do it, because I do think that anyone that wants to can do it. And even if you don't like math or something, or you don't like, that one class you took, that is not the be all and end all of science. And so I think it's unfortunate when people are kind of pushed away from the field because of a bad experience. And yeah, if you're really serious about getting involved in science as a profession and into academia, I would encourage you to, just reach out to people and kind of work as widely as possible and figure out what interests you and what excites you, because there's just so much out there to do and to study.
Nora, thank you so much for coming on the show, and we really, really appreciate it.
Thank you so much for having me. It's been a lot of fun.